Hello and welcome to the fourth week of this course. So far we have studied about the data collection, data summarization and data visualization. Now before moving on to the data analysis part, today we are going to learn about an important concept of sampling distribution, which is going to help us in making inferences based on the data. Now, what is sampling distribution? Sampling distribution is basically the probability distribution of a sample statistic. And today we are going to see how the distribution of this sample statistics varies with the different situations. So first of all, we are going to learn about some important terms which includes population parameters and sample statistic. Then we will consider a situation where we will be drawing a single sample from a population, and then based on the sample statistic, we would be finding out the sampling distribution of the sample mean, of sample variance and sample proportion. So as you can recall, mean and variance are used for your numerical variables and proportion is used when you have a categorical variable. So keeping that in mind, we will move ahead and we will start with the first important term, that is population. As you all know, population is basically the entire group of individuals or objects in which we are interested. Here, the numerical characteristics of the population are referred to as the population parameters. So these population parameters are in fact fixed, but they are unknown. That is why our interest is in understanding or gaining the information based upon it. How do we do that basically? Suppose you are interested to know the average income of people living in your community. Since you cannot go and ask and collect data from each individual, what you can do is possibly that you will collect a random sample from it, and then based upon that sample, you will study the same characteristic that you wanted to study about the population. In this example, suppose you were interested to find out the average income, then in this sample, you will find out the average income, and then based upon it, you can generalize it to the entire population. And that is why your sample is basically a subset of the population. Okay, our goal is to extract meaningful information from the population, or you can see that our goal is to estimate these population parameters. In order to do so, we take a sample and then based upon the sample, we make an estimation about the population parameters. For instance, it could be the population mean or the population variance. So this sample is going to give us the correct information. Now it might happen that if your sample is not representing correctly, then some errors might arise. Okay, so as you can recall, in the first week we studied about this concept of probabilistic and non-probabilistic sampling. So if you draw a random sample, then only whatever conclusion you draw based upon the sample, that you can extend up to the population, or you can generalize it for the population. You can say that, okay, the average income is going to be 50,000, suppose. If it comes out for the sample, it is 50,000, then you can say that on an average, the population income or the average income of all the individuals living in that community would be around 50,000. So to make such a conclusion, you need to draw a representative sample, or you can say that you need to draw a random sample. So, which brings us to our next question, that is, what is a random sample? See, whenever we say that we have n independent and identically distributed random variables, and they are coming from the same probability distribution, it is referred to as a random sample. So if you hear the name or the term random sample, then it should immediately click to your mind that we are talking about IID random variables. That is, xi's are IID random variables. Independent means that outcome of one is not going to impact the outcome of the other. And identical means that they are coming from the same population or the same distribution. It means if you're talking about normal distribution or the normal population, then all these random variables have been taken from that only. All these random variables follow normal distribution. And as you know, for random variables, we use the capital letters, that xi's or yi's. And once you know their actual value or the realized value, then you replace these corresponding xi's by the small xi's. So let us understand this. If your x1, x2, xn, these are your independent random variables identically distributed, then it means that in the context of your average income example, suppose you decide that you would be taking a sample of 1000 individuals, and to each of them you are going to ask their average income. So x1 is basically the income of the first individual, x2 will be the income of the second individual, and likewise you will collect up till 1000 individuals. Okay, and to each of them you would ask them their income. Obviously, in your city, there must be more than 1000 people. Since we cannot collect data from each and every individual, we are just focusing on this some random number that I have taken over here, 1000. So this is the random variable corresponding to the income of the first individual. This is the income corresponding to the second individual, and likewise we will move up till here. Now, suppose you come to know that the income of the first individual is, suppose, say 50,000, okay, and the other one is 30,000, and likewise you keep on getting these answers, and finally suppose this is 45,000. Then how do you represent this? You use the corresponding small letter xi's. This one would be x2, because this is now the realized value. The random variable has now taken the exact value, because here this is not hidden to you. You now know what is the exact income of that particular individual. So it is no longer random, and you know it exactly. So that is why you can write x1, x2, and it will go up till 1000. If you want to write the joint density, then basically, since they are independent for all of these, it is just the product of their marginals. So that is why you have these small xi's over here, because these will be the realized values. Okay, whatever the PDF is, in that you can just replace it with this xi's, small xi's, and you will get your answer. So this is about the random sample. So random sample basically refers to independent and identically distributed random variables. Okay, so we just now have seen this. The next term that comes is your statistic or your sample statistic. Okay, so sample statistic is basically a function of the random sample itself, provided it is not a function of any unknown population parameter. So it can be any function of the sample statistic, it can be any function of the random sample. You have taken out xi's, right? And you can define any function as long as it is not containing or it is not a function of any unknown population parameter. You would refer to it as a sample statistic. For instance, if you have the sample mean, so here you have x bar as 1 over n summation xi. This is a function of the random sample because x1, x2, xn, these are the IID random variables that you have taken, and now you are defining sample mean, which is a function of these, and it also does not involve any unknown population parameter also. Likewise, you can have sample variance also and sample median also. So in this case, as we have seen, sample mean, capital X bar, 1 over n summation xi, where I goes from 1 to n. If you want to find out the sample mean in this data set, then you would be writing x bar, where here you will replace n by 1000. Okay. Initially you would write this. Now once you have observed the sample, in that case you would substitute the values and you will get some x bar over here. Now whatever you get, that would be the sample mean or the average income. And from based upon that, provided it satisfies certain criteria that we will learn as we move ahead in this course, you could say that, okay, this is going to be estimating or a good estimator for your population parameter. Sample mean, or you can say sample variance. The other one can be your range also. So range is what? As you know, it is the difference between the smallest and the largest observation. So when we write this round bracket over here, it refers to the largest order statistic. So if you are given some 10 observations and you arrange them in an increasing order such that x1 is less than x2 and so on, then we can say that x ordered 1, that is the smallest order statistic over here. Okay, this is the smallest observation, and this is your, at this position, whatever you have, that will be the largest one. So range is basically the difference between the minimum and the maximum. So that is why, again, this is also sample statistic because it does not involve any unknown population parameter. Now you could think of a situation that suppose you have x1, x2, xn, which are coming from normal with the mean mu and variance sigma square. We are interested in mean. So I could come up with this statistic. Here sigma square is unknown for us, suppose. In this case, this won't be your sample statistic. Why? Because here you have this sigma square which is unknown to you. Had it been known, then it would have been perfectly fine. But since we are finding a function of the random sample, but it also involves the unknown population parameter, that is why we say that it is no longer a sample statistic. Okay, so for population, we use population parameters. These are the terms. Okay, population parameter, we denote population mean by mu, variance by sigma square, and when we take a sample, then we refer to it as a sample statistic. And the corresponding notations, so here for population proportion, it can be P. So here you will write sample statistic would be this, sample variance is this, and sample proportion, for sample proportion you can use P hat. So these are the commonly used notations. And you can see that whenever we are talking about a statistic, mind it, it is not statistics, the subject, it is statistic, which is basically a function of the random sample. Now, see that whatever sample statistic you are defining, right, here in this case, suppose x bar, what is happening over here? This is basically a function of the random sample. So whatever sample that you would take, it will depend upon that. Now the sample, if you change even a single observation, then the sample mean is going to differ. So this sample mean over here itself acts as a random variable. And since it acts a random variable, it will have a distribution of its own. Hence, the probability distribution of these sample statistics, okay? So the probability distribution of the sample statistic is basically referred to as the sampling distribution. So now we are going to begin with our first theorem, which aims to find out the expectation and variance of sample mean. So here we consider that we have a random sample from a population with mean mu and variance sigma square. Then expectation of sample mean will be mu. If we take the variance of the sample mean, it comes out as sigma square by n. And if I take the expectation of the sample variance, we get the population variance, that is sigma square. So here, if you see one important thing, in the first and the third one, here we have kept within the expectation, this is a sample statistic, okay, sample mean, and here also in the last one, this is sample variance. And on the right hand side, we are getting sigma square, that is the population variance, and we are getting population mean. Okay, so if you take expectation of the sample statistics and you get the population parameter, the corresponding population parameter, then it is a very desirable property which is known as unbiasedness that we will study in the next week's lecture. So let us now try to prove these. Note that here we are saying that we are taking a random sample from a population. We are not specifically saying which population. So these results hold for any distribution that you might think of. Okay, so in all the cases you would get these three results would hold true. So let us see the proofs of these one by one. The first theorem over here says that if you have a random sample coming from some population with mean mu and variance. Now, what does this mean? Here, when we say that xi is a random variable, is a random sample, then it means that each of them are IID random variables, right? So it means that expectation of x1 if I take, this will be mu. Similarly, if I take expectation of x2, this will also be mu, and so on. This thing would continue for nth random variable also. So all of these xi's, since they are IID, all will have the same mu. Similarly, if you look at the variance, then variance of first observation, this would again be same as variance of the second random variable, and this will keep on continuing till xn random variable, and all of these would be same as sigma square. So now with this assumption, let us first target and solve the first problem, that is, we have to prove that expectation of sample mean is basically population mean. Now what is sample mean? So let us start from the left hand side. Expectation of x bar, which is, instead of x bar, I could write 1 over n summation xi's, where I goes from 1 to n. Now, since expectation of ax, we know that if a is any constant, a would come out, and it's same as expectation of x. So in this case, since n is a constant, that would go outside, 1 over n expectation of x summation xi, so I can instead write as x1 plus x2 and so on up till xn. Okay, they are independent. I can take the expectation inside, so this would be expectation of x1 plus so on up till expectation of the last one, right? Each of these xi's, we have seen just now that all of them have the same expectation because they are identically distributed. So this would be 1 over n. Each of them have the same expectation, which is mu, and these are n such terms. So this would be n times mu, which basically gives us the population mean. Okay, so this, you can see that the proof is very simple. You start with this. You have just substituted what is the sample mean, and you just simplified, keeping in mind the assumptions that have been made, and then you would get the result. Likewise, this second conditions or the second proof is that variance, if I take the variance of this, then it would be sigma square by n. To prove this, so this is basically your proof. If I have to prove this, we can again start from the left hand side. So variance of x bar, so I can keep 1 over n summation xi's. where I goes from 1 to n. Now what is happening over here? Since variance of ax is same as a square times variance of x. I believe everybody knows this result. So here n is a constant. When you take it outside, then it will become variance 1 over n square. And again, you will have variance of x1 plus x2 and so on up till xn. Okay. They are independent, so there will be no covariance term. I can take the variance inside. So variance of x1 and so on up till variance of xn we will get. Each of these variances is sigma square. So you will have n times sigma square because you have n such terms. So 1 over n square into n sigma square. So this would basically mean that it is sigma square by n, which is your right hand side. A random sample from any population whose mean is mu and variance is given to you, then if you take expectation of the sample mean, you will get population mean, which means that on an average, you are going to approach your population mean. It will be very close to the population mean. Similarly, if you are calculating the variance of that, variance of the sample mean would be sigma square by n. So it gets divided. So the original variance is sigma square. Population variance is sigma square. But if you are talking about variance of sample mean, in that case, it gets divided by n, whatever is the sample size basically. Now, we move on to the third proof. It said that it is providing over here a relation between sample variance and population variance. Okay, expectation of sample variance is same as this. Now, what is sample variance and population variance? Sigma square, we all know it is 1 over n, we can write 1 over n summation xi minus mu whole square, right? We have seen earlier also. But when we talk about the sample variance, we are talking about sample, so this would be replaced by small n. And here, we don't just write n, instead we write 1 over n minus 1 summation over here xi minus x bar whole square. So population mean is replaced by the sample mean and rest of the things remain same, with just the difference that now in the denominator earlier you had the population variance, population size, but now here you have sample size minus 1. The reason why we have minus 1 would be evident through the proof, and let us begin that now. So expectation of the sample variance. So here it means that we want to write expectation of 1 over n minus 1 summation I goes from 1 to n xi is minus x bar whole square. Okay. Again, n minus 1 can be taken outside. So this will be 1 over n minus 1. Expectation would go inside. Then you would have summation I1 to n xi minus x bar whole square. Okay. Now, first let us try to simplify what is in this bracket over here. So let us just focus on this part first. So summation xi minus x bar whole square, where I is going from 1 to n. Here, if I add and subtract mu, then also it would remain the same, no difference. Now you consider this as one term and this, and then expand this. So here you will have summation I goes from 1 to n So here the first term would be xi minus mu whole square plus mu minus x bar whole square plus 2 times mu minus x bar into xi minus mu. Fine. Now if I take the summation inside, you will have the first term as summation xi minus mu whole square. Okay. Now what will happen in the second term? These are constants. So summation, instead of that I can write n times mu minus x bar whole square plus twice mu minus x bar, and summation when applied to this is what over here? Summation xi minus mu. What is this term? Summation, if you take inside, this would be summation xi minus n times mu. Okay, and what is summation xi? Since x bar is 1 over n summation xi, so summation xi, this would be same as n x bar minus n mu. And I can take outside. So this basically leaves us with x bar minus mu. Okay. Or you can take a minus and you can write it as mu minus x bar. So I can write minus of this n times mu minus x bar. Because here also we have mu minus x bar. Now, let us see what is the term that we have. Summation xi minus mu whole square, I goes from 1 to n. So here you have plus n mu minus x bar, this term, and here it will be minus, so let me just write that, plus n mu minus x bar whole square, and here it will be minus 2n times mu minus x bar whole square. Okay. So you see that this term and this term is same. So basically we are left with I going from 1 to n summation xi minus mu whole square minus n times mu minus x bar whole square, or I can also write as x bar minus mu whole square because this is a square term, so it won't be affected. Fine. Now you are left with these two options. Let us now substitute it back to this expectation over here, right? So we had 1 over n minus 1 times expectation we are taking inside. So first you have expectation of summation xi minus mu whole square minus n times expectation of x bar minus mu whole square. You can take expectation inside this. So this would be summation I1 to n expectation of xi minus mu whole square minus n times expectation of x bar minus mu whole square. Now what are these terms with the expectation? This one over here and this. If you recall, what is variance of a random variable? Variance of any random variable is basically expectation of x minus expectation of that random variable whole square. Okay. So if I consider variance of xi, it would be expectation xi minus expectation of xi. Since by the assumption of this theorem, each xi has the same expectation, which is mu. So you will have this. Fine. So this is nothing but variance of, this is variance of xi's. And what is this other term? If you consider variance of x bar, then it would be expectation of x bar minus, because x bar we have already proved in the first part that x bar has expectation as mu, so it will be same, right? So this part is nothing but variance of x bar. So now we can continue with this 1 over n minus 1. Here you have summation I1 to n variance of xi's. So each of xi's has variance sigma square. So it will be n times sigma square minus n times variance of x bar is what? In the second step we have obtained that variance of x bar would be sigma square by n. Okay, so we will substitute that over here. Now what you are left with is n will cancel, so n minus 1 will also cancel out, and you will be just left with sigma square over here. So you have proved that if I take expectation of the sample variance, you would get the population variance as we have obtained over here. Now here you can notice that if you would not have taken sample variance over here as n minus 1 and instead you would have taken n, then it means that here everywhere, let me just use a different color, everywhere this is extra, right? Minus 1. Everywhere this would be gone and you will be just left with just n, right? Here also you will have n and here also you will have n. Then in that case, you would not be getting sigma square as the final answer. You would have got n minus 1 times over n minus 1 over n sigma square. Now, this would not be an unbiased property. Since we need it to be unbiased, this change has been made in the sample variance formula itself so that n minus 1 gets cancelled out and you are just left with the population variance. So that is why we make over here, sorry. So here we have written n minus 1 summation xi minus x bar whole square. So we have seen from a given population, if we are drawing a sample, its mean remains the same, variance becomes sigma square by n, and furthermore if we look at the sample variance, then it gives us the population variance on an average. Likewise, you can also find the moment generating function also. Okay. So let us see what is the result over there for moment generating function. So we have seen the proof of this. Now the second theorem says that if you are drawing a random sample from a population with MGF like this, it's a moment generating function, this is the notation, of random variable x at t, then basically the moment generating function of the sample mean is nothing but, if you calculate the moment generating function of each xi at t by n, instead of t you will have t by n and raised to the power n, because they are identical, each one of each xi's will have the same MGF because they are coming from the same population, they are identical. So that is why instead of having moment generating function of xi's into the second one, you would just have the same MGF as the base and you will raise it to the power n. So let us see how do we prove this. So now we want to prove the MGF. And the result says that MGF of the sample mean at t is basically moment generating function of x at t over n whole to the power n. So let us begin with the left hand side and prove it. Now, moment generating function of x bar, by definition of moment generating function, we know that it is same as expectation of e raised to the power t x bar. Had it been just x, so you would have written expectation of e raised to power tx. Since you have sample mean over here, you will write x bar. Now, instead of x bar, you could simply write what it is. X bar is what? X summation xi by n. So you can write it x1 plus x2 and so on up till xn whole divided by n. Okay. You can consider these terms as expectation of e raised to the power t x1 by n the second term would be likewise there, e raised to the power t x2 by n, and so on it will continue till the last one, expectation of e raised to the power t xn by n. Now if you look at these, what are these individual terms over here? This is basically the moment generating function of the random variable x1 at t by n, right? Because if you have mx moment generating function of a random variable at t, this is nothing but expectation of e raised to the power tx. So using that same thing over here, by definition, you would get that each of these correspond to xi's, right? This is the moment generating function of x2. This is for the xn. Now, since you know that all these xi's are identically distributed and they are coming from the same population, their MGF would also be same. That is why instead of writing moment generating function of x1, moment generating function of x2, you could simply write moment generating function of x at t by n and since there are n such terms, you would raise it to the power n. Because all the xi's are identically distributed, you would get this. So it will be raised to the power n. So this power is not appearing over there. So whole to the power n, that is what you have the result. So this is your result. It will be raised to the power n. So we have seen that if you are drawing a sample from a population, what is a sample statistic in that case? It depends upon the problem that which sample statistic that you want to take. It could be sample mean, sample variance, or sample proportion. And then we have seen two theorems where we are talking about taking a random sample from any general population. Here we are not specifically saying that it is coming from some normal population or something else. Okay, so far whatever results we have established, they hold true for all the populations.